So we've talked a little bit about the generative approach to classification, and today we'll put it to use. We'll look at a simple one-dimensional data set which has three classes in it, and we'll see how we can classify this data by fitting a Gaussian distribution to each of these classes. So here's the problem that we're dealing with. We have a bottle of wine, and we like it, but its label is missing, and so we want to figure out which winery it is from. 1, 2, or 3. We're going to take the machine learning approach and we'll measure some visual and chemical features of the bottle of wine and use this to predict the label, 1, 2, or 3. Now we have a training set to help us, and this training set was obtained from 130 bottles. 43 of these bottles were from winery 1, 51 from winery 2, and the remaining 36 were from winery 3. For each of these bottles, a data point was measured consisting of 13 features. Now, these are features that make sense to wine experts, things like flavonoids and proline and magnesium levels. Okay, but there are 13 such features, and so the data points are essentially 13-dimensional vectors. So we're going to use this data to build a classifier that takes the features from a new bottle and predicts the label, 1, 2, or 3. And there's also a separate test set with 48 labeled points that we can use to evaluate how good our classifier is. Okay, so let's quickly recall the generative approach to classification. So what we need to do here is to fit a distribution to each winery individually. Okay, so for winery 1, we fit some distribution, say P1 of X. For winery 2, we fit a distribution P2. And we have a distribution P3, which captures the data from winery 3. We also need to know the probabilities of each of these labels. Okay, so what percentage of the data, what percentage of bottles come from winery 1? That's by 1. What percentage of bottles come from winery 2? That's by 2. And by 3. Okay, so these pi's add up to 1. And once we have all this information, that's our model. When we get a new bottle of wine, X, we get its feature vector, that's the X. And the class we predict, 1, 2, or 3, is simply the class that maximizes phi j times pj of X. Okay, so in this case, because there are 3 classes, we simply compute pi 1 times p1 of X, and then we compute pi 2 times p2 of X, and pi 3 times p3 of X. And we take whichever of these is the largest. Why do we do that exactly? Well, this is a direct consequence of Bayes' rule. Okay, so we have this new bottle whose features are X. We want to know what its label is. And so the label we're going to pick is the most likely label given X. Okay, so what is the probability that the label is J given the specific feature is X? Using Bayes' rule, it's the probability of having label J times the probability of seeing X in label J divided by the overall probability of seeing X. Okay, so the probability that the label of J is just pi sub J. The probability that we would see X amongst the bottles from winery J is Pj of X. And the denominator doesn't depend on J at all, so we can ignore it. So we're simply going to pick the label J that maximizes this equation over here. And that's the generative approach. Okay, so let's go back to the data now. Right, so this is a summary of our data set. And the first thing we need to do is to figure out the probabilities of each of the individual classes. So out of the 130 bottles, 43 of them are from winery 1. That means the probability of winery 1, the weight of winery 1, is 43 over 130. Okay, so pi sub 1, the weight of winery 1, is 43 over 130, which is about 0.33. Out of the 130 training bottles, 51 are from winery 2. So the probability of winery 2 is 51 over 130, which is 0.39. And likewise, the probability of binary 3 is 36 over 130, which is 0.28. And as you can see, that these three numbers add up to 1. Okay? So that part's easy. And in general, fitting the class weights is very easy, almost trivial. The harder part is fitting a distribution to each class. Now in this case, the data consists of 13 features. So it's a 13-dimensional data set. So we need a distribution over 13-dimensional space. We haven't yet seen how to do that. And so let's just simplify things for the time being and just pick one feature out of the 13. Okay, so we have these 13 features. We're just going to pick one of them. Let's just go ahead and choose alcohol level as our feature. And so we've now reduced the data to just one dimension. And we're curious, how well can we predict the winery using alcohol level alone? Okay, good. So now we need to fit one distribution to the alcohol levels from winery 1, another distribution to the alcohol levels from winery 2, and a third distribution to the alcohol levels from winery 3. What one-dimensional distribution should we use? Well, the default choice is the Gaussian. Okay, so let's look at it. The Gaussian in one dimension is just the familiar bell curve. It's a distribution that is specified by just two parameters, a mean and a variance. I'm going to be denoting the mean by the Greek letter mu and the variance by the Greek letter sigma squared. Okay, so the mean is mu. I'm just going to emphasize it by rewriting it. And the variance is sigma squared, which means that the standard deviation is sigma. We're going to refer to this distribution by using the shorthand n of mu sigma squared. The Gaussian with mean mu and variance sigma squared. The n stands for normal, and people call it that because a lot of data looks like this. Okay. Now, this particular distribution is a distribution over real numbers. Its density is given over here by this formula. The density might look a little bit messy or complicated at this point, but believe me, it will start seeming a lot more familiar as time goes on. Okay, so what can we say about the distribution? So first of all, it is centered at the mean mu. That's right here. It's symmetric about the mean. About 2/3 of the distribution lies within one standard deviation of the mean. About 95% of the distribution lies within two standard deviations of the mean. Okay, so it's a distribution that's fairly well concentrated about its mean. And these are the distributions that we're going to be using. Okay, so we need to fit a Gaussian to the data from each of the wineries. Let's start from winery number 1. Okay, so we're using just one feature, alcohol. And if you remember, we had 43 bottles from this winery. So we have 43 numbers, 43 alcohol levels. And what I'm showing over here is just a histogram plot of these numbers. As you can see, it's very jagged, as a histogram always is if you have very few data points. Okay, so how do we fit a Gaussian to this? Well, to fit a Gaussian, we just need to figure out the mean and the variance. So we take our 43 numbers, the 43 alcohol levels, and we compute their mean, and we compute the variance. That's very quick. It's just 2 lines of code. And what do we get? This is the distribution we get. The mean turns out to be 13.72. The standard deviation is 0.44. Okay, so sigma is 0.44, which means the variance is the square of that. Sigma squared is roughly 0.2. And this is what the distribution looks like. This red line is the density that we fit for winery number 1. As you can see, it's a nice smooth distribution compared to the lumpy mess that we started with. Okay, so this is what we've done for winery 1, and we're just going to go ahead and do exactly the same thing for winery 2 and winery 3. And this is the result. Okay, so we already talked about winery 1. For winery 2, it turned out that I think we had 51 bottles, so 51 numbers, and their mean was 12.3, and the variance was 0.28. And for binary 3, the mean was 13.2 and the variance was 0.27. Okay, and you can see the three curves over here. These are P1, P2, and P3, the distributions for each of the three classes. Okay. Now, are these distributions nicely separated from each other? No, not really. In fact, they're kind of on top of each other. And this really gives us a hint that using this one feature alone, we are not going to be able to classify binaries very accurately. But let's go ahead and see what we get anyway. Okay. So given all this information, given the stuff in this, given these pies and this P1, P2, P3, how do we classify a new bottle of wine? Okay, so we get a new bottle of wine, we measure its alcohol level X, okay. And then we pick the answer J, 1, 2, or 3, for which pi j times pj of x is the highest. Okay, so for example, let's say that our new bottle of wine has an alcohol level of 15. So it's over here. Which one are we going to pick? Well, the black and green ones, that's wineries 2 and 3, have almost zero density at that point. So we're going to pick the red one, winery number 1. What if the bottle of wine has an alcohol level of 11? Then we would pick winery number 2, the black one. What if it has an alcohol level of something like 12.5 over here? What would we pick? Well, we wouldn't pick the red one. We'd pick either the black or the green. Okay, so this is a case in which winery 2 and winery 3, those two distributions, P2 and P3, have roughly the same density. So which one would we pick? Well, we would pick winery number 2 because it has the higher class weight. Okay, so remember we are multiplying these two numbers together. So in that case, if the alcohol level is something like 12.7, we would end up picking winery number 2. Okay, so we do all this, and what kind of performance do we get? It turns out that the test errors, we had a test set of 48 points. This misclassifies 14 of them, and so the test error is 29%. That's not very good, but it's way better than random. Okay. Well, so we have seen our first classifier using the generative approach. Its performance was somewhat mediocre because it was based on a single feature. When we throw in a lot more features, we'll be able to improve its performance dramatically. But in order to see how to be able to do this, we are going to delve a little further into probability.